All right, so the first thing I notice is that, yeah, I'd say these functions, they either have one or two turning points based on the graphs. So does every cubic function have the same number of turning points? I would say no. But they do have either one or two. Or two turning points. How do the number of turning points of a cubic function differ from the number of turning points of a quadratic function? Well, remember quadratics, they either have a minimum or a maximum value. So quadratics only have one turning point. Okay. And then are the graphs of cubic functions symmetrical? So are they symmetrical? Does that mean, like, for example, on a quadratic function, you could draw the axis of symmetry and it's going to be symmetrical on both sides. What do you guys think for cubic functions? Are they symmetrical?
They have like down the center. Oh no, you can fold them over.
Right, so you could do some, yeah, you could fold them. Like, for example, let's take a look at this green one here. Yeah, I could draw a line and a vertical line, and I could fold it over, or I could do like a horizontal line. I could fold it up and then fold it over. So there's some truth to that symmetry there. But when I get to some weirder ones, like let's see, like this one, is this going to be symmetrical? Can I fold this one symmetrically somehow? Trying to think. I mean, like that one I think is a little tougher to justify symmetrical. This one I think is a little tougher to justify symmetrical. So it's like there's some that maybe are symmetrical. This one, these ones, it's harder to say, right? But what do you guys think? Are they symmetrical?
I mean, they follow the same shape, but like it goes in a different direction.
Right. So yeah, same shape, but a different direction. So maybe not perfectly symmetrical. Okay, I think that's a good way to put it. Okay. So some of them do. Some of them are symmetrical. But it really depends just when we're looking at that graph. Okay. So yeah, you can say they follow the same shape, but it really depends. All right, what type of symmetry do they have? That's where we'd have to kind of, like I said, we folded it twice, right? We would fold it up and over. So you have to fold over the x and y axis. If that makes sense what I'm saying there. Whatever works best for you to describe, this is the wording you kind of want to use to describe it. All right, so if me talking about folding doesn't make sense to you, don't just write down what I'm saying, write down what makes sense to you for your own description, right? I should just be going over this at the end. I shouldn't be answering these questions for the first time for you. All right, do the graphs of cubic functions all have a maximum and minimum turning point? We can say not all of them. But some of them do have those local maximum and minimums. Local maximum and minimum points. We'll say min and max points, okay? And then roots, that's the same as zeros. That's the same as x-intercepts. Does every cubic function have the same number of roots? So do they all have the same number of zeros, the same number of x-intercepts? Yeah.
No,
So
because you can have like 3, 2, or 1, or 0.
yeah. Well, you can't have 0 with a cubic function. You're actually gonna have at least 1.
Oh,
So
really?
yeah. So the idea
Yeah,
is
one has to go down.
yeah. So there's a slight difference between zeros and x-intercepts. And the way it works is zeros, all cubic functions have 3 zeros. All cubic functions have 3 zeros. All right. The big thing is x-intercepts are just writing the zeros as ordered pairs, and when I say they all have zeros, they could have imaginary zeros, which means they won't have an x-intercept. All right, or they could have multiplicity of zeros, which is the same zero multiple times, which we've talked about before in AGS3, and we might have talked about it a little bit last year. So that's a possibility as well. X-intercepts, they can have 1, 2, or 3. Or they can have, actually it's just 1 or 3. I don't know, 1, yeah, 1, 2, or 3 x-intercepts. None of our examples today had 2, but yeah. And again, if I go back to my Desmos screen, I'm going to switch over one more time to Desmos. It depends on the multiplicity. And then...
Wait, so there's 3 zeros for that one?
This one would have 3 zeros, but it has 2 imaginary zeros, and I can tell just because it goes straight through, so that's a multiplicity of 1, and then it would have 2 imaginary zeros. All cubic functions, or third degree polynomial, they're all going to have 3 zeros. And imagine...
sorry, would it be like the max and the minimum point of like that local turning point, and then like the thing that's also hitting the x-intercept?
Actually, the nice thing is for imaginary zeros, we don't even need to worry about it because the IB exam will never test you on imaginary numbers. So I'm just pointing out that all cubic functions will have 3 zeros, and imaginary zeros always come in pairs. There's always going to be, like if I factored this and factored out the first 0 as negative 2.18, and then I used the quadratic formula to find the other 2, I'd get a negative number inside the square root when I was doing the quadratic formula, which is why they'd be imaginary zeros. So all cubic functions will have 3 zeros. Sometimes they will have imaginary ones. Problem 3, this is going to be another multiplicity 3 problem, so it's going to have 3 real zeros. All of them just happen to be at the same point, 5, 0, so it's only 1 x-intercept. Problem 4, multiplicity 3, because it slows down as it goes through. Problem 5, this one's a tricky one. So it doesn't slow down until after it goes through the intercept. So this one's another one where it's going to have 1 real zero and then 2 imaginary zeros, because it doesn't slow down until after it goes through the x-intercept. Problem 6 has 3 real zeros, and they're all multiplicity 1. That's kind of a nice one to
over
see.
this like in class, because I don't really remember that.
You don't really remember this? No, it's fine. Like I said, the IB exam is not really going to test us on this. What I'm going to ask you to do on your test on Friday is maybe sketch one of these and identify the x-intercepts, or write it in factored form, and we will talk about that type of stuff. Okay.
Okay, thanks.
Yep. And then the last one, multiplicity 3, and look at that, it has 3 real zeros. All right. That's what these problems look like. Okay, problems 6 and 7 are the ones where they have 3 real zeros, and you can see all 3 of them have multiplicity of 1. Otherwise, there's a multiplicity of 3, there's a multiplicity of 3, there's a multiplicity of 3. All right, and then there's 1 real zero, 2 imaginary zeros, and then there's 1 real zero, 2 imaginary zeros. All right, so a couple different examples there of the different types of problems we could face. Excuse me. All right. Parameter generic cubic function. For starters, when we have this written as ax cubed plus bx squared plus cx plus d, this is called standard form. All right. And the parameters, one of the most important ones is that a cannot equal 0. which is the first coefficient, the leading coefficient of the first term. And that's because if a equals 0, this is a quadratic function, not a cubic function. So that's why we say a cannot equal 0. All right, so that's the general idea with cubic functions, identifying multiplicities, identifying zeros, things like that. And we'll talk about how to write it in factored form as well, which we did talk about factored form with quadratics last week. Okay, so big things with cubic functions. I have it written down right here. I just stole this from your textbook. Cubic functions are polynomial functions where the highest power of x is 3, and a, b, c, and d are real numbers. All right, that'll create a cubic function. What I'm going to ask you to do...
So are real numbers like every number that's like 1, 1.1, like negatives, everything?
Yes. Yeah, anything that's a decimal, a fraction. You could have irrational numbers in there, so pi could be a real number. It's just not imaginary numbers, which is like negatives and square roots. Those are the only imaginary numbers.
So it doesn't include negatives?
It does include negatives, but not negatives inside of square roots, because those would be imaginary numbers. But -6 is a real number, so that would work. Yeah. Okay.
So anything decimal, negatives, fractions?
Yep. Those are all real numbers, yeah.
Excuse me, sorry, could you scroll up a little bit just so I could see question 6?
Yeah, so this box here that says cubic functions are polynomial functions where the highest power of x is 3. That's kind of got the important information. And again, it does state a does not equal 0 because we don't want to deal with a equals 0 because then it's a quadratic function because we would just have 0 times x cubed and this part would go away. And we're really just dealing with an x squared problem. All right. The way your textbook writes a lot of things for this section is it will say, sketch the graph y equals f of x. So it's basically saying f of x is the y value, which we already knew. And then on your sketch, I want you to label the coordinates of the points where the graph has intercepts. So it's x and y intercepts, basically, is what this part's asking. And then any minimum or maximum points, maximum or minimum points. And you just label those points as well. All right. So for parts A and B, I'm just asking you to go ahead and sketch the graphs and identify those intercepts and mins and maxes. Okay. So go ahead and work on those two now. So that's what these two graphs are going to look like for problems A and B for example 10. All right. There's a little note down here as well that says for one-to-one function, one-to-one cubic function, you can sketch the inverse, f inverse of x by reflecting the graph of y equals f of x over the line y equals x. So you're over the line y equals x, you sketch the inverse of the graph. The key here is it's got to be a one-to-one function, and one-to-one basically means your graph's going to do two things. It's going to pass the vertical line test, all right, and it's going to pass the horizontal line test. That would make it one-to-one, which means if I'm looking at example A, it would pass the vertical line test because it's a function. Example B also passes the vertical line test. But if I'm doing the horizontal line test, on example A it passes, but on example B, if I go like right here, I see 1, 2, 3 points that are sharing the same, 3 different x values that are sharing the same y value. So example B is not a one-to-one function. All right. So whenever we're doing inverse functions, we're only ever going to do inverses in this class of one-to-one functions because we want the inverse to also be a function. Because if I took the inverse of graph B, it's not going to pass the vertical line test, which means it won't be a function. That's what that one-to-one means. Okay. So it says for each of the following graphs, use the vertical line test to determine if these are functions. Use the horizontal line test to determine if these graphs are one-to-one. All right, so why don't you guys try examples A and B, and then just write your notes right below them. So are they functions? Yes or no? Are they one-to-one? Yes or no? Okay. Does it pass the vertical line test? Does it pass the horizontal line test? All right, so example A is a function. It's not one-to-one. Example B is a function, and it's also one-to-one. All right, so real quick, the equation of example B here is going to be written down like this. Y equals x minus 5 to the third power. Or we could say f of x equals x minus 5 to the third power. If I wanted you to find the inverse algebraically, okay, and you remember, this is a little throwback to AGS3. We did it a little bit last year too in IB in first semester. What do we do first with when we're finding the inverse? What do we do with our x's and y's?
You flip them.
You flip them. So the first thing we do is we say x equals y minus 5 cubed. And then we solve algebraically for y. So we take the cube root of both sides. And the cube root of y minus 5 cubed is just going to be y minus 5 cubed, or y minus 5. And then the last part is we add 5 to both sides. So cube root of x plus 5, 5's not in that cube root, equals y. And we could say, oh, that's f inverse. The cube root of x plus 5. All right. So that's how you would do finding an inverse algebraically. You got to be able to show me your work algebraically to find an inverse. I've already written the test for Friday. So hint, hint, there might be one question that asks you to find the inverse algebraically on something. Okay. Yeah, believe it or not, I actually got ahead this weekend because I was able to get my grading done reasonably quickly. So yes, I would expect something like this on the test on Friday, finding an inverse algebraically. All right. And then if we sketched the graph of the inverse, it would literally just be switch all the x and y values. So there was a 5, 0, that becomes a 0, 5. There was a 6, 1, that becomes a 1, 6. There was a 4, negative 1, that becomes a negative 1, 4. And it's going to look something like this. And that's what our graph of our inverse would look like. Reflected perfectly over the line y equals x. All right. Okay. So now, example 11 says, find the inverse of the following functions algebraically. Sketch each function with its inverse to confirm that they are symmetrical about the line y equals x. So what I would say...
Inverse of the first one?
What'd you say?
There is no inverse of the first one?
No, there should be inverses of both of them. So find the inverse of both of these functions algebraically. What I want you guys to do is first find the inverses, and then go to either Desmos or your graphing calculator and sketch both the original and the inverse. And then you can use your graphing calculator to sketch. All right, so for these two graphs, I went ahead and showed you algebraically. I skipped some steps on part B just because I was out of space. But the first one is going to be the cube root of x plus 2. This time, the plus 2 is inside the radical. That's the big difference between inside and outside the radical. All right, the second one, we had a lot of steps. We had to first subtract 5 from both sides. Then we had to divide both sides by 4. Excuse me. Then we take the cube root, and finally we subtract 1. So we end up with this f inverse equals cube root of x minus 5 over 4, and then minus 1 at the end. All right. And we should be able to get a quick sketch of our graphs. All right, and again, you just type it into your calculator, type it into Desmos, whatever you want, and sketch yourself a quick, give yourself a quick sketch of the graph. And it'll look something like that. And then the inverse, just move it in the opposite direction. It's gonna look something like that. There's your inverse. All right, and you label both of them if you're using a pencil or something, just that way I can tell the difference between your regular graph and your inverse function. All right. Example 12 is going to take us a little bit of time, so I'm going to not sketch B from example 11 right now, just for time saving sake.
We need to label the points like on the test and stuff of like the inverse and like what the original is.
Should we? Yeah, we should label the graph just like that. We can just do a quick sketch and then do a quick label. If I ask you to label the intercepts and things like that, then please label those. All right, so I'll be specific on a test. Say, please label these points. All right, please sketch this. Just do that, okay? That's what you should expect. All right. So example 12 says a can of cat food has a volume of V equals 200 centimeters cubed.
Are we gonna label part B or no?
No, we're not going to do that right now just because of time. I just got to get started on the next problem. I don't want to keep us too much past 11 or past 11 at all, actually. So we're just going to move on to number 12. I'll do part B at the end if we have time. So the radius of the can is R centimeters and the height is H centimeters. So this is what our cylinder is going to look like. Do the center. There's your radius right there. And then your height is going to look like this. And then what I have drawn next to this, I found this online. This is basically what the cylinder looks like if I were to fold it out on a flat piece of paper. So this is a cylinder flattened on paper. And it's basically a rectangle and two circles. If I were to lay out this entire cylinder, just roll it flat, it'd be a rectangle. And then the two circles would be the top and the bottom. All right. So it says, explain why pi r squared times h equals 200. And for this first part, pi r squared times h, that's actually the equation for volume. Pi r squared h. You might remember area of a circle is always pi r squared. And that's what we're doing here. Is we're saying, hey, we're going to find the area of a circle. We're going to do pi r squared. Area of a circle, pi r squared. And then we're going to multiply it by h, which is the height. And that's where the volume comes in, pi r squared h. So it's saying pi r squared h equals 200. So that is the volume of a cylinder equation. And then it says, rearrange the equation from part A to make h the subject. This is a question that the IB exam loves to do. Solve for h algebraically. So it's just like how we just did an inverse before. Now we have to get h by itself on one side. So I have to divide both sides by pi and divide both sides by r squared. And I'm going to end up with something that looks like this. H equals 200 over pi r squared to get h by itself. So now I have an equation that's just in terms of height. So if I know what the radius is, I can find the height. Okay. Now the next one, this is why I came up with finding this box for us so we could see what the cylinder looks like flattened. Because it says, go ahead and find an expression for total surface area of the can. So surface area means we're finding the area of each individual part. So, like I said, the area of the circle is going to be pi r squared. That's the area of our circle. the area of the other circle, that's circle 1, circle 2 is also going to be pi r squared h. And because it's a cylinder, they should be the exact same. So technically the area of the circles, both circles, is just 2 times pi r squared. We could just say there's one circle, and then you multiply by 2, you're going to get the area of both circles together. The next is we have this rectangle. Next thing, we have the rectangle, which is height h. And you know what the length is of the rectangle?
Radius?
What'd you say? It's not radius, it's actually...
Perimeter or circumference?
It's circumference, yeah. It's the perimeter of the circle. So circumference was 2 pi r, right? Which is also happens to be the length of this rectangle. So whenever you do area of a rectangle, you do length times width, or in this case, length times height. And the length is 2 pi r, and the height is h. Okay. So if I wanted to find the total surface area, I'm going to do 2 pi r squared plus 2 pi r h.
Wait, where did the 2 pi r h come? What's the or circumference is 2 pi r?
Yeah, so circumference of a circle is 2 pi r, which is the perimeter of the circle, which is the same as this length here. That's what's happening. So we're doing length of the rectangle times the width of the rectangle, which is, in this case, the height. So length times width is 2 pi r h. Kind of weird, right? And so that one's a tricky problem. This is just example 12 from your textbook, which I think is a really difficult problem, which I thought was kind of weird because this textbook isn't known for giving crazy difficult problems. But I thought part C was a really hard part on this particular problem. What's going to happen now, though, it's a substitute your expression for h from part B into your expression for S, so your total surface area. I guess, yeah, we'll call it S instead of A, area of the total, just because that's what your textbook was doing. And then show that S equals 2 pi r squared plus 400 over r. So this is a show that. Show that is another big thing you'll see on the IB exam. So again, we had the 2 pi r squared, which makes sense. That's the area of the two circles. And then it says, go ahead and substitute for h. We had 2 pi r, and then we know that h is going to be 200 over pi r squared. And what happens is I'm trying to get this to equal 400 over r, this second part. Well, I know pi divided by pi is 1. R divided by r squared is going to get rid of one of the r's in the denominator. We're going to be left with an r left in the denominator. And then 2 times 200 is 400. And that's how we end up showing that this equals that. Which again, that's a really weird part, because part C I think is kind of a hard part to find the expression for the total surface area of the can. But then part D does the show that, and the show that's a big part of it. I wouldn't say the show that I think is a good IB question, but part C I don't think is a good IB question because the IB exam likes to build it. So if you can't figure out part C, you can still solve part D, if that makes sense. So I think that's kind of a leap for part C to D. But part D, being able to manipulate equations, and part B, being able to rearrange an equation, those are huge like IB questions that you could expect on an IB exam. So you should be able to do those parts B and D. Part C, like I said, I think is a little bit of a reach, but IB question. All right. Just to give you an idea for those of you who are planning on taking the exam this year. All right. And then using suitable scales for your axes, plot the graph of this equation. So now it wants you to plot this equation right here. But if I were to plot this, I need to turn it into X and Y.
Wait, isn't it plus 400 over R?
What'd you say? Sorry, what'd you say?
Isn't it plus 400 over R, not equal?
Yes, thank you.
For part D, isn't it plus 400 over R?
It is plus 400 over R. Yes, thank you. So now what we're doing for part E then is I need to graph this. I'm going to say this is y equals 2 pi x squared plus 400 over x. I'm rewriting it in terms of x's and y's, where r equals x and s equals y. So that way I can graph this on Desmos. If I don't do that, it'll be really confusing to me how to do this on Desmos. But pi is a number, so I can definitely use pi, no problem. And when I'm done graphing this function on Desmos, I need to play with my scale a little bit. It's going to look really weird, but it looks like I'm going to need to create a scale that's going to go like for y up to 1,000, down to negative 1,000, x probably just 20 to negative 20. But the big thing I really want to catch on my graph here is right around here where that minimum value is. So when I sketch it, it's going to look something like that. On the negative axis, which isn't real world, we don't need to worry about it too much. It's going to look something like that. But I want to be able to find that minimum point here. And that minimum point was 3.169, comma 189.322. And again, I said that r equals x. So, hey, r is the radius, so that's 3.169 is the radius part. S equals y. So in the last part it says, hey, find the surface area, the minimum surface area. So the smallest the surface area can be is 189.322 centimeters squared. And then what's the corresponding radius that could happen? Find the value of the radius for which this occurs. 3.169 centimeters is the radius where that occurs. All right, last problem here. Sunset High School track qualified for an international track competition. And we have this equation. There's a little typo in it. It should say 0.75 t right there, okay? So 1.75 plus 0.75 t. And we're going to do the height of the shot put, find the height of the shot put after 5 seconds. So the first part is we're going to plug in 5 to the equation and solve for the shot put. And when I solve for 5 here, it ends up saying, oh, Petra's height of the shot put was like 3.9375 meters. All right, that's if I actually plug it in my calculator and solve this equation. So it's just basically saying, hey, when Petra throws the shot put, the maximum height it's going to get to is 3.9375 meters. Basically, a good way to think about this is you're throwing the shot put at time 0. It's going to make a big old arch. It's going to come back and it's going to hit the ground. All right. And then this is your height of the shot put here. So that's our maximum value right there, was the 3 point at 5 seconds was, actually it's not even necessarily the maximum height, it's just the height at 5 seconds. So we'll go ahead and say the height at 5 seconds, probably somewhere over here, 5 comma 3.973 meters. Okay. And then the last part says, find the times when the height of the shot put is 3 meters. So now this one, we're basically going to graph y equals 3. So we're going to graph y equals 1.75 plus 0.75 x minus 0.0625 x squared. And then we're going to graph y equals 3, and we're going to find the intersections. And the intersections for this problem, once we put that in our graphing calculator, we look for them, we should get x equals 2 x equals 10. Or in this case, it's basically saying t equals 2 at 2 seconds and at 10 seconds are when that shot put's going to be at 3 meters in height. Okay? And that covers everything for today. So I hope you guys have a great day, and we'll see you tomorrow.